F1 wants us to find the average slope. Remember, at each of the points on this blue curve, the slope is something different. And then the average slope, though, it says the average slope from x equals -3 to x equals 17. The average slope, it's pretty easy to find the average slope. It is just the slope of the segment connecting the 2 points would give us the average slope. So the average slope on the interval -3 to 17 is equal to, it would be whatever f is at 17 minus whatever f is at -3 all over 17 minus a -3. That's just the change in y over the change in x. That's the traditional way that we find slope. So at 17, the y value is -2. At -3, the y value is +5. And then we have 17 minus a minus, so +3. And that comes out to be -7 over 20. That makes sense because this pink line has a negative slope. Specifically, the pink line has a slope of -7 over 20. Now in F2, it's actually the same exact thing, but we're reviewing some of this notation. It wants to find the average f prime of x. So in the beginning, we said f prime is slope. So asking for average f prime is the same exact thing as asking for average slope. This time it wants the average slope on 4 to 12. So I've drawn it in pink, the average slope. So all of these slopes are not whatever the average is. There's a slope along different points. The slope keeps changing. That's the idea here of a derivative, is the slope keeps changing. But the average slope is the slope of the line connecting the 2 endpoints of the interval in question. So for some formal notation, it would be the f value at 12 minus the f value at 4 over 12 minus 4. That's change in y over the change in x. So that would be 9 minus 8 over 12 minus 4, or 1 over 8. That's the average slope. You can see here, rise over run, we rise 1 while we run 8. Change in y over change in x. Now this is my absolute favorite part of the lesson. For each of these in G, you're going to find or estimate the thing they have indicated. G1 flat out says, find the slope of f at 4.5. So 4.5, it's here. See, that lies on a linear segment, and to find the slope at that point is the same way we found the slope in Algebra 1. It's change in y over change in x, and so the answer to the slope at 4.5, we can say m equals, to see that rise over run, that's -2. All right. So next it wants to know f prime at 3. Now f prime of 3, the only thing that's new in this unit about f prime of 3, let's find that here. F prime at 3 is that I have to know that that is asking for the slope of the segment at 3. Now this one is not as easy to eyeball rise over run, so I'll do my change in y over change in x using 2 points around it that I know. So remember, we have a line segment here because the initial graph told us that's a linear portion. So it's going to be the change in y, so 8 minus 2.75 over the change in x, which is 4 minus 2. And that comes out to be 5.25 over 2, or if I simplify it, 2.625. This value here is exactly what the slope is. There's no estimation. This is exactly what the slope is. There is no estimation because I have line segments there. Now for this one, it says dy dx. Again, another notation for slope. but this one means the slope at the x value equals 0. So I'll come over here, and when x equals 0, here's a point on the graph. Now I have to estimate that slope. Do you see by eyeball that it looks like we have a horizontal tangent? So it looks like the slope is 0. Do you see that horizontal tangent looks like this, and the slope of the horizontal tangent is 0. So we're estimating, again, estimating by eyeball. This is an eyeball estimation that the slope is 0. Next, we want to estimate or find f prime of 4. What does that mean? It means the slope at x equals 4. So I'll come over to the point when x does equal 4, and oh, look at this. Do you see what I see? The slope was positive, boom, and then the slope sharply transitions to a negative. We call that a corner. It's a sharp transition, and when you have a sharp transition, there is no slope. So it's undefined, or we can simply say the slope does not exist. There is not a slope when you have a sharp transition. Do you see that that would also happen here? There's a sharp transition, so there's no slope at x equals 14. Finally, G, looks like I said G13, but I mean G5, which is f prime of 13. So f prime of 13, let's locate that point. 13, ooh. So this is a curve section. It's not linear, it's curved, so I can eyeball it, but there is a standard way to estimate the slope. And what you do to estimate a slope that's in between 2 points, you look at the 2 points around it that are definitely defined. So this point is defined, and this point here is defined. And if I connect those 2 points with a line and find the average on that, what we call a small neighborhood, then that would be a good, an approved estimation for the slope at the point in between them. So let's just reiterate that. So at 13 is where I'm trying to estimate the slope. If I pick 2 points around it, one at 12, one at 14, and I find the slope connecting those 2 points, that will be an acceptable way to estimate the slope at the point in the middle. That's called the average on a small neighborhood method. So it's going to be approximately the average on the small neighborhood. F of 14 minus f of 12 all over 14 minus 12. Change in y over change in x on the neighborhood around the point in question. What does that give us? 2 minus 9 over 2, or negative 7 over 2. That estimates the slope of the tangent to the curve here, or estimates the instantaneous slope at the point x equals 13. Now for H. H wants us to estimate where we have horizontal tangents. Horizontal tangents, that just means where the slope is 0. We've identified one already right here, horizontal tangent. Not a horizontal tangent here because it's a sharp transition, so we would say there is no tangent. But there is here, horizontal tangent. Ooh, missed one down here, horizontal tangent. Not here, sharp transition. So those would be the smooth vertices, horizontal tangents. So that's going to be at x's approximately, let's say 0, 6.5, and then again at 10. So that would be f has a horizontal tangent, slope 0, at approximately x equals 0, x equals 6.5, and x equals 10. Part I wants us to show the appropriate notation where the function here does not have a slope, does not have a derivative. Remember, slope, derivative, same thing. We talked about this already. There is not a derivative or slope there, sharp transition. There is not a derivative or slope here, sharp transition. You may wonder whether there was a sharp transition here or not, but that was ruled out because the initial information told us that there was a smooth transition here. Also, the initial information told us that there was a slope at this point that I'm circling in yellow. So we know there is a smooth transition there. So the guessing game was taken out of those two yellow points. Okay, so pardon me. Let's answer the question. At F does not have a defined slope at x equals 4 and x equals 14. Now we're going to just show some notation. Let's not do overboard here. What I want you to know is that there's a sharp transition. We can make this some wacky notation. We could say that f prime from the left of 4, well, that's a positive number. And we can say that f prime from the right, or as we approach from the right, the slope is negative. The important part here is that f prime from the left of 4 is not equal to the slope from the right of 4. So this is some advanced notation for us to say that the slope from one side is equal to positive and the slope from the other side is negative. They're not equal, therefore there is not a derivative, there is not a slope. This was at x equals 4. At x equals 14 now, similar analysis. The difference, though, it's not that one is positive, one is negative. They're both actually negative. F prime from the left of 14 is negative, but the important part is it's not equal to the slope from the right of 14. So just introducing this notation. I wouldn't worry too much about this right now, about the notation, but do know about the sharp transition means you do not have a slope.